students, welcome to class 12 physics plus. In last class we also discussed this one, so here today I will start with that topic also. Once I will discuss then this one, force on a current carrying conductor in a uniform magnetic field, then we proceed to the next topics of this chapter. So as earlier we also know this formula F equals to B into I into L sine theta, or F equals to Bill. In short form, you can remember the expression of a force on a current carrying conductor in a magnetic field. Okay, and here it is the derivation also be written over there, how it we can derive, or you can follow this one. Then this is from one book, one reference book also be there. I will collect from that reference book. Okay, so just once in short, I will just explain its derivation. Here you see that in this figure, PQ is a conductor having length area L and area of cross section is A, and it carrying a current I along positive Y direction. As shown in this figure, the current will flow along positive Y direction. So the magnetic field along positive Z direction, the magnetic field also acts along a positive Z direction. Now the electrons drift towards left from the velocity Vd. We know that the direction of electrons is opposite to the direction of current. So if the current flows in a positive Y direction, so we can say that the electrons will move, or that means this velocity we already discussed in our current electricity chapter, the drift velocity, what happened inside the conductor, then and due to what we get the current. So current will the electrons will drifted in opposite direction of the electric current with the velocity Vd. Vd is a drift velocity. That's why it is written over there, the electrons drift towards left. That means the opposite to the direction of current with the velocity Vd. Now, each electron experiences a Lorentz magnetic force along positive x-axis. We already discussed the magnetic Lorentz force and how we can understand the direction, that formula also. If we apply this thing, so we can understand that the magnetic Lorentz force will act along positive x-axis as shown in this figure, and this force is F equals to minus E into Vd cross B, because we get the formula F equals to Q into V cross B. So here we talks about the electron, and electron has negative charge, that's why we can write minus E, and Vd is a velocity. Here the charges velocity when the charges move inside a magnetic field, that velocity. So here the electrons will be drifted with a velocity Vd, so that's why in place of V we can write Vd cross B. Clear? Okay. Now we consider if n, small m, is the number of electrons per unit volume, or it can be said as electron density. Density means mass by volume. So mass is the number of free electrons, and divided by volume gives us the electron density. So small n is the number of free electrons per unit volume, or in place here you can write the like here in this slide it will be written over there, n is the number density of electron. Number density of electron. Okay, so the total number of electron in the conductor, n is the number density per unit volume, the free electrons are small n, then the total electrons inside the conductor of L length, that is n equals to small n into its volume, n into A into L, n into A into L. So the total force on the conductor, that is capital F, whatever the Lorentz magnetic, that force F as shown in this figure, you see that is capital F along the x-axis. So F equals to N into F, magnetic Lorentz force, and if we put this expression over there, we get this expression E into N into A minus L VD cross B. This expression we get. Now here this I into L represent the current element. In this figure you see that this is the I into L. This is represent the current element vector in the direction of current, and then the vectors L and VD will have the opposite direction. So we can take minus L into VD, that is equals to VD plus VD into L vector. So in place of minus L into VD, you can write VD into L. So we get the force expression F equals to E into N into A VD L cross B. Now E into N into A into V, in current electricity we studied this one. This is called current expression we get in current electricity chapter. We also proved this one. So in place of E into N into A into VD, that is equals to I, so we can write F equals to I into L cross B, and this is a vector form of the force on a current carrying conductor in a magnetic field. So because cross product is there, so if we write this expression as a vector scalar form, so F equals to I into L into B into sine theta. Because cross product is there, so cross product means sine theta. Theta is the angle between the direction of magnetic field and the direction of flow of current L and B. So here also some special cases also be there. As theta equals to, we also discussed in a last video this special cases, same thing is here also. Whatever we get for 0 degree and 180 degree in our last video, or 90 degree we get the maximum force, here also we get the same thing. Theta equals to 0 degree or 180 degree, so sine 0 0, sine 180 also 0, so the force is 0. Thus we can say that the current carrying conductor placed parallel to the direction of the magnetic field does not experience any force. That's why in this figure we consider the current will flow in a positive y direction and the magnetic field along the positive z direction, perpendicular direction, because all axes are perpendicular to each other. And why we consider this one? Because in when the these two are in a perpendicular direction, the direction of current and direction of magnetic field, we get a maximum force, or the conductor will experience a maximum force. That is a second case. Theta equals to 90 degree. So sine 90 value is 1. So if we get F equals to B into I into L, that is the maximum force. So current carrying conductor, if it will be placed as perpendicular direction to the magnetic field, it will experience a maximum force. Here? Okay. So how we can understand the direction of force? We already discussed using the Fleming's left hand rule. If we stretch our thumb and first two fingers of in our left hand mutually perpendicular direction, so if forefinger represent the direction of magnetic field, middle finger represent the direction of current, then thumb will gives us the direction of force on a conductor. In this figure, if you apply the Fleming's left hand rule, you also get the direction of force along positive x-axis. You apply your left hand rule, your left hand rule, and like this way, which finger points here, it will be mentioned. You can see that the thumb will represent the force and it is along the positive x direction. Clear? Here one numericals I will also add, you can understand, then that's why I will add this one. So in this expression, F equals to B into I into L, the unit, it is SI unit, force is in Newton, current I is in ampere, length L of the conductor, it is in meter, and the magnetic field B is in Tesla. You have to keep it in your mind. Okay, so this numerical, this here the magnetic field expression is given, and it is mentioned that a wire of length L carries a current I along the x-axis. So current will flow in a x-axis. A magnetic field exists in a space. That expression also be given. We find out the magnitude of the magnetic force on the wire. That means F. So B equals to B0 I hat plus J hat plus K hat Tesla. So the magnetic force on the wire, we know that this formula F equals the vector form, because I, J, K is there. So we use the vector form I into L cross B. Clear? Okay. Now in place of B, if we put this expression, and it will be I, okay, I into L I hat, because x-axis, so I hat it is, and in play, because the vector, any vector quantity will be represented by its magnitude as well as its direction. So in place of L vector we can write L into I hat. So L represent its magnitude, I hat gives us the direction of L vector. So I into L is L into I hat cross B0 into that one, the expression of B. So if you solve this one, you get the last expression, that is K hat minus J hat B0 I into L. Try to solve in your home, or try to if you don't understand, then you tell me, because you have, I think, I hope everybody remember that the formula of cross product of the orthogonal vectors or the unit vectors or the base vectors, that is I cross I, it will be 0, J cross J it will be 0, K cross K it will be 0, and I cross J, two different vector, the cross product of two different vector gives us the third vector, third unit vector. So I cross J gives us the K vector, J cross K gives us the I vector, K cross I gives us the J vector. So we apply that formula here also, and we get the last expression. So now if we find out the magnitude, that means root over of F equals to root over of fx square plus fy square plus fz square. So like this way, and b0 I into L, it is constant. So we get root 2 b0 into I into L Newton. This is the magnitude of magnetic force. Okay, I think you understand this one, and here I will give some numericals. Try to in your home, answer also be given, and if you are facing any problem, please let me know that which number you have problem, so I will solve this one and upload. Okay. Okay, so now the application of this force F equals to BIL sine theta for two parallel current carrying conductor, parallel also, anti-parallel also. We get the concept from, if we find, once we find out the expression for two parallel current carrying conductor, then you can conclude for parallel current attract and anti-parallel current repel each other. Parallel current attract and the anti-parallel current repel each other. Okay, so let's start with its derivation. And it was first discovered by Ampere. This force between two parallel current carrying wire, it is first observed by scientist Ampere in 1820. That two parallel straight conductor carrying currents in the same direction attract each other, and those carrying current in opposite direction repel each other. So you have to remember that the same direction current attract each other, opposite direction current repel each other. How we can derive this one? So here in this figure you see that we consider two parallel wires. First figure, okay, first figure, both having the same direction, that means a parallel current, and the second one is an anti-parallel current. So first figure, if you consider the first, that is right hand side figure, left hand side figure. So here we consider two long parallel wires AB and CD carrying currents I1 and I2 parallel to the, that means two wires are parallel, that means current also be the parallel to each other. and the separation between these two wires, that is R. The separation between these two wires, that is R, as shown in this figure. Okay, so because here we get the magnetic field produced by current I1 at any point on the second wire, and same thing also we get the magnetic field produced by current I2 and at any point on the wire AB. So first we find out the magnetic field produced by I1 on CD. So here in this figure you see that we considered any point and the magnetic field B1 on the figure, on that figure, that is mu 0 I1 by 2 pi r, because these two are the long, infinitely long wire, and for infinitely long wire we know that this expression of magnetic field is B equals to mu 0 I by 2 pi r. Okay, so what you consider here? Consider two infinitely long parallel wires AB and CD carrying currents I1 and I2, and the separation between them or distance between these two wires will be R. So due to current I1 on the wire CD at any point, the magnetic field is B equals to B1 equals to mu 0 I1 by 2 pi R, and this field is perpendicular to the wire CD, and if you apply the right hand thumb rule, you see that it will points into the plane of the paper normally, into the plane of the paper normally. So you can use the cross sign also in the diagram. You can also give the cross sign. So whenever the magnetic field is induced in the wire, or magnetic field is created in the wire CD, on the wire CD, it will exert a force. It exert a force on the current carrying wire CD using the Fleming's left hand rule. Okay, so the field acts perpendicular to the wire and its direction, or it points into the plane of the paper. So it exerts a force on CD, and this force, if you apply the Fleming's left hand rule, you see that the force direction is towards AB. The force direction is towards AB. That means towards AB means it will attract. Okay, so let's first we see that the expression of that force acting on length L of the CD, of the wire CD, that is F2 equals to BIL sin theta. So I2 L into B1 sin 90 degree, because due to I1, B1 amount of magnetic field is induced or produced on the wire CD. So F2 equals to I2 L B1 sin 90 degree, theta is 90 degree. So here if you put the expression of B1, that is mu 0 I1 by 2 pi r, so ultimately you get mu 0 I1 I2 by 2 pi r into L. This is a force acting on length on the wire CD. And if we find out the force per unit length, that is small f, so that is equals to F2 by L. Per unit length, the force small f, that is equals to F2 by L, and that is equals to only L is cancelled, so mu 0 I1 I2 by 2 pi r. Now according to the Fleming's left hand rule, this force acts at right angles to CD towards AB. You also apply the Fleming's left hand rule, you see that the force direction is towards AB. Towards AB means we can say that the AB will attract the wire CD towards itself. So that's when the current in the two wires are in the same direction, the forces between them are attractive, and it can be seen that F1, that is equals to minus of F2. You try to in your home that you find out the expression of F1. You try to find out the expression of F1, and if you apply the Fleming's left hand rule on AB due to CD, you see that the F1 direction is towards CD, that is opposite to the F2. So we can write F1 equals to minus of F2, and minus sign means as when the currents in a two parallel wires flows in a opposite direction, sorry, F1 minus F2, F1 equals to minus of F2, that means it will be attractive. So you do this one, okay, you do in your home, try to find out F1, find out the expression of F1. Its magnitude will be same, dissimilar, that means mu 0 I1 I2 by 2 pi r, you get the force per unit length, but the direction of F1 is opposite to the direction of F2. You see this one, and whenever you apply the Fleming's left hand rule. Now if we talks about the second figure, where the current are in a opposite direction in AB, and through the CD the current are in a opposite direction. So what happened, we see that the direction of forces are opposite, that means far away from each other, not towards the wire. The in this figure you see that CD, the F2 force is outward direction, F1 force also be outward direction, not towards the wire. That means they are repel each other. And you also get this expression, and you, if you apply the Fleming's left hand rule, you also find out like this way, you can also find out the expression or the magnitude of the force acting on AB or the CD. So from here we can say that whenever the current in the two parallel wires flow in the opposite direction, that means anti-parallel to each other, the forces between the two wires are repulsive. From this diagram we can also understand, and mathematically also we can understand. Try to in your home. If you are having any problem to find out or unable to understand how you can find out, please let me know in a comment box. So I will make another one video with this all. F2 is already find out for the first figure, then I will find out F1 and for the second figure also. But please write in a comment box that if you are unable to understand how you can find out. Clear? So from here you can understand parallel currents attract each other, anti-parallel currents repel each other. Now from here, from this expression or from this derivation, we can also define ampere. How? Take I1 I2 equals to 1 ampere, and the distance between them is 1 meter, all one. Whenever we define anything in a physics, all the quantities we can consider as a 1 as per their respective units also be there. So R equals to 1 meter, so we get F equals to small f, also small f, force per unit length, mu 0 by 2 pi. I1 I2 1, R is 1, so F equals to mu 0 by 2 pi, that is equals to 2 into 10 to the power minus 7 Newton per meter inverse. So how we can define this one? Define 1 ampere. 1 ampere is that value of steady current which on flowing in each of two parallel infinitely long conductor of negligible cross section placed in vacuum at a distance of 1 meter from each other produces between them a force of 2 into 10 to the power minus 7 Newton per meter of their length. Whatever the force will be produced in between them, that is 2 into 10 to the minus 7 Newton per meter, because that is force per unit length. So the unit also be Newton per meter of their length. Okay, so here also I will give some numericals related to this force F equals to V into I into L sine theta. So try to in your home. Same thing, if you facing any problem, please let me know which number you have problem, or that derivation also I will already discuss, and in each and every video I will I told that if you are having any problem, please let me know, or please write in a comment box. Otherwise how can I know that which topic or which point you cannot understand if you don't write in a comment box, or if I I'm unable to understand that which point you are not understand. Clear? Okay, so the next point, next topic of this chapter, that is torque experienced by a current loop in a uniform magnetic field. So in electrostatics, we also want to find out the torque experienced by a current loop in a uniform electric field. Now here, uniform magnetic field, if you placed any loop, any closed circuit, so what will be the torque experienced by this loop? So let's start. In this figure, you see that we consider a rectangular coil PQRS. You see this PQRS. Okay. We placed it in between a uniform magnetic field. Uniform magnetic field means magnetic field lines are parallel to each other. And this coil will suspend it in a uniform magnetic field B with its axis perpendicular to the field. The dotted line, it is its axis, and with respect to its axis it will be rotate, or it will suspend it. Okay. Now here if we consider the I is the current flowing through the coil PQRS, and small a and small b are the sides of the coil PQRS, because it is a rectangular coil. So one is the length, another one is a breadth. A into B gives us the area of the coil, capital A. Capital A is the A into B. This is the area of the coil, because rectangle length into breadth gives us the area of the rectangular surface. And theta is the angle between magnetic field and the normal to the plane of the coil. Theta is the angle between the direction of B and the normal of the plane, that is represented by N, to the plane of the coil. Now here inside PS and QR, the sides PS and QR are equal, or are because its length is A, both having length is A, are equal but opposite. Because through PS and QR the direction of current is different. Both are the parallel, but the current will flow in the opposite direction. So if we apply the according to the Fleming's left hand rule, if we apply it on these two sides, we see that the magnetic forces also on this PS and QR are equal but in a opposite direction. So what happened? The resultant is 0. These two forces are cancel each other. So this is for PS and QR. So for PS and QR, the resultant force is 0. So now if we talk about the side PQ, if we apply the Fleming's left hand rule, we see that the force, it will experience a normal inward force. The force will act inward direction. Force will act inward direction. You try to you just stretch your left hand. Fleming's left hand, according to the Fleming's left hand rule, you stretch that 3 finger. So you can understand the direction of the force. You can understand the direction of the force. It is inward direction. It is inward direction. Try it now. So you just stretch. So you know which point the forefinger points the direction of magnetic field, and the middle finger is the current. So the thumb, you see that you just move your right hand like that way. According to this figure, you see that the thumb will represent inward direction, and its magnitude is, we know that, B into I into L. Now if you talks about the side RS, this is for PQ. Now for RS, The same force is acts of not the equal forces apply on also apply on the side RS. But if you apply the Fleming's left hand rule on RS, you see that the direction of force is outward direction. On PQ it will be inward direction, and on RS it will be in opposite direction, that means outward direction. So these two forces are equal. Uh, that means the magnitude is equal but the direction is different. So these two forces form a couple which exert a torque on this loop. As you, if you compare with the torque which you studied in electrostatic, there also you get the two forces acting on a acting on it, that is one minus QE and another one is a plus QE, which is in a opposite direction, and this two magnitude is same. So it will form a couple which exert a torque on that loop. So same thing is here also. So torque means force into perpendicular distance. So force is magnitude is B into I into L, and perpendicular distance between this between the sides, that is A into sine theta. A into sine theta. So you get I into AB into A sine theta. Here this is the, yes, I into B into A sine theta. Now if we consider there are n number of turns, just multiply it with a n, tau equals to n into I into B into A sine theta. Now n into I into A, this is represent as m, small m, and this is called magnetic moment of the loop. N into I into A, this is represent as small m, that is called magnetic moment of the loop. So that expression we can write tau equals to mb sine theta, like the dipole moment P. Here that in that expression in electrostat we get one expression, that is 2 into Q into A. In place of 2 into Q into A we write P. P is sine theta, we get this one. Okay, so here in place of n into I into A we get we can write m, small m. So this m is called magnetic dipole, magnetic moment of the loop, and so tau equals to, we can write in vector notation, m cross b, small m cross b. The direction of torque is depends on the m cross b, the direction of m cross b. Clear? So m is the magnetic moment. Magnetic moment. Okay, now here some special cases also be there. If theta equals to 0, tau equals to 0, that means torque is minimum when the plane of the loop is perpendicular to the magnetic field, and the plane is placed as a perpendicular to the magnetic field. So theta equals to 0, because normal and B, then in that condition it will be in the same direction, so theta equals to 0. Now theta equals to 90 degrees, so torque equals to n into B, I into B into A. That is a maximum for torque when the plane of the loop is parallel to the magnetic field. Thus we can say that tau is the maximum, that is n into I into B into A. Just these two things you keep it in your mind when we get the minimum torque and when we get the maximum torque. When the loop is perpendicular to the magnetic field we get the minimum torque, and when the loop will parallel to the magnetic field then we get the maximum torque. Understand? Okay, here it is in a short form, it can be written over there from one slide. So same thing, this and this thing are same, which one you have preferred, that things you can write. If this things is understandable to you, then you can write these steps also, otherwise you can write these steps. Clear? Okay, and here this theta is theta, you keep it in your mind, this theta here, theta is the angle between the normal of the plane of the coil, and that means the axis, okay, and the magnetic field theta, okay. And in vector form, here n is the capital N is the n number of turns, that's why tau in vector form also n written over there. If you consider only one turn, then tau equals to only m cross p. In some books, that's magnetic dipole moment or magnetic moment, it is written as capital M. In some books, it will be written as small m. So whatever the notation you use, just mention over that what is its meaning. That m is capital M or small m. So as per my opinion, you use the small m. Okay, small m is the magnetic dipole moment. Magnetic dipole moment. Clear? Okay, so just a few topics are left of this chapter, that is a galvanometer. In next video we complete that chapter and that topics and some numericals related to that galvanometer. And whatever the numericals in this video I will give, that try to solve in your home. If you are facing any problem or if any point you are not understand, please write in a comment box. So I will make a one video, separate video with this, with that doubts. Okay, so have a nice day. Tata, bye bye.